Okay, in the second half, we're moving on to 18C, and it's called rules for differentiation. So far you guys have been working through what's called the derivative from first principles. Okay, and the first principles is just to show you guys like how originally derivatives are calculated. Okay, but you won't be using that for unit 3 and 4. There is a much easier way of doing it. It's funny how none of you guys actually complained about how long that process was, because most of the time I got complaints about that process, and when everyone gets to the rules, they're like, why didn't we learn this initially? Well, the idea is you learn how to do it properly, and then you learn the faster way of doing it, right? So for the rules of differentiation, okay, remember how previously we've got a few examples. Fx is, let's say, x squared, right? Okay, I'll use a table format here. So one column is fx and the other one is f dash of x, which is the derivative, right? So this is the derivative, okay? If fx is x squared, then f dash x is 2x. And we learn another one. Let's say if we have fx equals to 3x squared, then f dash x is 6 times x. So we've done these two before, and then if we got, say, 4x, it would just be 4. I'll give you guys a few more, right? Pay attention. I'll give you guys a few more examples and see if you can figure out the pattern, okay? Without looking at the answer first, try to figure out the pattern yourself. It's actually not that hard. Okay, the next one is, if I get 3x cubed, the derivative will be 3x power 2. Okay, all right. The next one, if it's x power 4, the derivative is 4x power 3. You guys see a pattern here?
Yeah.
Yeah? Okay, Charlie, you try. Next one, if fx is x power 5, what's the derivative?
5x 4.
5x power 4, that's right. Okay, Sarah, do you see a pattern here? Yeah? Sarah, what is x power 100 when you derive it?
100x 9 to the power of nothing.
Yes, that's right. You bring, so you guys know the pattern already, right? You bring the power down, and then you multiply by the power, and then you drop the power by 1. Okay? So now I'll test you guys on some slightly harder ones. So let's say, Charlie, what is the derivative of 6x power 3?
18x squared.
Yeah, 18x squared. Very good. So this is essentially, it's just 6 times and then 3x squared, right? Yeah, so you derive just the x version because 6 is a constant factor. You learn that later, that you can just simply take the constant factor out and then multiply that back in. Okay, and how about, okay, let's try a tricky one. Sarah, what is the derivative of 5x power negative 2?
Negative 10x power of 1.
No. Try again. What's the power here? Charlie?
Oh, negative 3.
Yes, negative 3. You drop it by 1. So minus 2, minus 1 is minus 3. Right? Okay? So so that's an example of a tricky one. Another one is, let's say you have 2x power 1/2. What's the derivative? That's a tricky one.
Like x negative 1/2.
Yes, that's right. X to the power negative 1/2. Very good. So the steps are, so this is, to get this one, you have to do 2 times and then you bring the power down 1/2, right? X to the power, then you drop the power by 1. So if you do 1/2 minus 1 is minus 2/2, which is minus 1/2. So the new power is minus 1/2. Okay? And then 2 times 1/2 is just 1, so that would just be x to the power minus 1/2. Does it make sense, Sarah? Yeah. So this question with like fractional power is a little bit trickier, but it's actually not too bad. Okay, that essentially is the main topic of this one here. Oh, now one more thing. When you derive, okay, if fx equals to 5, what's the derivative? What do you think?
0.
0, correct. But why? Why is the derivative equals to 0?
Because it's a straight line. like a straight horizontal line.
Yes, that is a good interpretation. It is a straight horizontal line, so the gradient is always 0, right? Because it's a straight horizontal line. Another way of thinking about it is this. 5 is 5 times 1, right? Right? And 1 is x to what power?
0.
0, that's right. Okay? So 1 is x to the power 0. And so you follow the same rule. 5 times 0 times x to the power minus 1. Anytime you have 0 times into anything, the answer is just 0. Does that make sense?
Yeah.
Yeah, because it's 5 times x power 0. Just remember that. So when you multiply the power down, 0 times anything is 0. That's why when you derive a constant term, you just get 0. Right, that's another explanation. Now let's quickly have a look at. Oh yeah. Okay. If you have x squared plus 2x, what do you guys think is the derivative? Hint, you work it out term by term. You work it out derivative of x squared. And then you plus that with the derivative of 2x.
So 2x plus 2x negative 1.
Close, plus 2. So, right, haven't shown you guys this version yet. So, if you have something like 3x, right, the derivative is 3. Okay? If you have a linear expression, it's just a constant factor, y. Same rule, so this is x power 1. So, that would be 3 times 1 times x to the power 0.
Yeah.
And that's just equals to 1.
So for that, okay, yeah.
Okay, make sense, Sarah? Yeah. So you just derive, like term by term. Okay, another one. If you have something like this, 3 times x squared plus 1, let's say x squared plus x, for example, right? How do you derive this thing? If it has a 3 times into the brackets, what do you think? What happens to the 3 there? What happens to it is it stays exactly the same. It will be 3 times something. Right? If it's a constant factor, you can take it out and then multiply it back in later. So essentially you can ignore that, derive everything inside it, and then you multiply it back in. So that'll be 3 times 2x plus 1. Does that make sense? Yeah? Charlie, make sense?
Yeah.
Yeah? Okay. So that's it. And one more thing. So if you have something that looks strange, like say x squared plus 2 times by x minus 1, how do we derive this? What do you think? How do we derive this? Like it's you've got a big term times by another big, big factor times another big factor. What would you do this?
Cancel out stuff, or would you?
How would you cancel? Expand it, yes. All right. The idea is you expand the brackets. Okay. So expand the bracket. So that will be times. It will be times that, times this, times this. That will be x cubed minus x squared plus 2x minus 2. Okay. Given this one here, what's the derivative of this whole expression? Okay, what's the first term in the derivative?
X squared.
Not quite. Remember, you bring the power down, then you drop the power by 1.
Oh, 3x squared.
3x squared. Sarah, what's the next term?
2 negative 2x. The power of. Oh, that's it.
Yeah, that's it. Yep. And then Charlie, next one.
Plus 2.
Plus 2. And then Sarah, next one. You derive negative 2, you get? 0. That's right. So that's it. Okay. So it's just basically derive each term. Right. So imagine having to do this, but with the first principle, the x plus h minus fx. Right. This one will be painful to do. Okay. You have to sub x in here, expand that, and all that jazz. So that's why once you learn this new formula, you don't really need to do first principles anymore. But remember, in the exam in Unit 2, you most likely will be asked to derive using first principles. Okay, so now now you guys have learned two versions, okay? The first principles version, first principles just means the first way of doing it, right? Before they figured out all these pattern thing. And then next would be the faster way, basically. There's no name for it, but it's just the faster way, right? The formula. Yeah. Okay. So first principles, f dash x would be to calculate lim of h to 0 of fx plus h minus fx over h. So this is a formula to do any kind of derivative, okay? Any kind of derivative. It doesn't matter what the function is, but the faster way, if say fx is equals to, let's just say a times x to the power b, right? Then the derivative, there is a faster way of doing it, which is a times b times x to the power b minus 1, right? It's just bring the power down and then drop the power by 1.
Yeah.
Okay, and times it to any factor that you have before that. And then it just do it for every single term in the expression. Done. Easy? Yeah? So this one is a lot easier. So I want you guys to it's actually really not too difficult. Okay, go to question 1 and just work it out. Alright, you guys have seen the pattern before. Just go to question 1 and start working it out. It's not too difficult. Alright, the answers are up there. You can have a look. Check your answers. If you got it all correct, just move on. Question 2. Alright, we'll just keep going. Practice these ones. It's not too hard. Okay. Shouldn't be too bad. Alright. Let's see. Yeah, so one's all good. So once you check the answer, make sure you put a tick next to it. Yeah, just to know that it is done. Okay. Alright. 2F. FG, okay. Alright, the answers at the back, but I'll prepare a next example for you guys. So the next set of questions will be slightly different. Not hard, so this topic I think it should be okay, it should be easy for you guys, but there's just a few things I want to mention. Alright, so 2H is the one that I want you guys to try and get up to. Alright, the final one. Not too difficult, but see if you can get the correct values for all of the terms. That's the main thing. Okay, alright. Okay, good. All right, I'll pause everyone here, and yeah, okay, I think everyone's already done anyway. So have a look at example 8. So they ask us to, example 8, right? Ask us to find the derivative of this equation here, okay? And then, thus find f dash of 1. Now, before you do this question, give me the interpretation. What does that mean? What does it mean by f dash of 1?
The derivative of it when like x equals 1.
Yes, correct. So that's the derivative, right? Derivative when x equals 1. Okay, give me another interpretation of this. What does that mean? That's correct. That's the first one. That's the first correct interpretation. Now, what does that mean?
The gradient at 1.
Yes, perfect. Okay, the gradient at x equals to 1. So this graph, let's say it has the shape like that, right? And at the point 1, whatever that is, so x equals to 1 here, right? If you draw the tangent line, right, the gradient of this line is equals to f dash of 1. Does it make sense, Sarah? Yeah, because the gradient, the derivative gives you the gradient function, which is to calculate the gradient at any x value. So f dash 1 just means the gradient at 1, yeah, at x equals 1. Okay, now work this one out. See if you can work this question out before I show you the final answer. So you find the derivative first, and then you sub 1 into the derivative. Okay, just be very careful when you substitute the value in. There are two equations, all right? So you have got the derivative, which is that one there, and then you've got the original, which is this one here, right? You need to make sure you sub into the derivative to get the gradient, okay? Because they're asking you to find f dash of 1 here. So that'll just be 9 minus 12, which is negative 3. So that just means that at the point x equals to 1, the graph is going down, right? It's traveling downward because the gradient at that point is going down, okay? Now, can someone give me the interpretation of f of 1? What does that give us?
Wouldn't that just be like the x coordinate for 1 is like 1, like on the graph?
Try again. I think you got the right idea. Try again. The explanation, there's some errors in there.
Like the value of x and y is 1, like, I don't know.
You got it swapped around. It's the value of y
Oh, sorry, yeah.
when x is 1, okay?
It always
So
throws me off because like f of x, then I think like 1 is like the x.
yeah, 1 is the x, that's right.
No,
1
I
is.
wanted the y value.
Okay, so y equals to, let's just say y at x equals to 1 is equals to f of 1, okay? So this is the y coordinate when x equals 1. Later on, you will be asked to calculate, oh, what's the y coordinate and the gradient at whatever x values, okay? So don't be confused, right? When you sub into the original equation, I call this one the original equation, right? Original equation. So when you sub into the original, you get the y value because y equals fx. When you sub into the derivative, you get the gradient, right, at the point. Okay, good. And start on question 3. Let's do as many as you can. Question 3.
For question C, is it just zeroed then?
Not 0. So C, so you got f dash x is 5, right?
Yeah.
Right, f dash of 1 means you sub 1 into x, there's no x. So it's still 5.
Okay.
Yeah, so think about it, Charlie. 5x is a straight line, right?
Yeah.
Yeah, and on a straight line, 5x is like that. The gradient is always the same.
Okay.
Yeah, which is a constant number. Right, so once you're done with 3, move on to 4. 4 is actually very similar. It's just they substitute a negative number here, so it's a little bit tricky. Okay, how's it going? Yep, looks about right. Double check your answer first before you move on. Yeah. Okay. Right. Yeah, good. Check all your answers. We're good? Yeah. Okay, move on to question 4. Yeah, so Sarah, what about your question? You on finish that and then move on to question 4. Yeah, I want to see how you guys do question 4. Just be very careful when you substitute the value in for question 4 because it's a negative value. So make sure you have brackets. Question 4D is the trickiest one. Make sure you be very careful and get the right answer. This one, okay. Alright guys, have a look at the screen. I'll just go through 2 more examples and then you guys can keep going with the questions. Okay, just very quick explanations from me. So first, right, example 9. When they ask for the gradient of the tangent line at the point 1, -2, so note that the only thing you need to pay attention to is the word gradient of the tangent. Means that's f dash x, right? And then at the point 1, -2 means at x equals to 1. Okay, so you actually only look at the number 1 here. -2 is the y coordinate. So you only actually care about the x coordinate. Okay, and that means that this gradient of the tangent line is equivalent to f dash of the x value, which is 1. Does that make sense, Sarah? Yeah, Charlie, all good?
Yeah.
Yeah, then keep going. But then example 10, now, have a look at this one. Example 10, I'll show this one first before you guys continue. The other notation. Charlie, pause, have a look. So for example 10, right? This is the first time you guys are seeing the use of dy over dx. And what's the rule here? So the rule is if you have an expression, let's say, so remember previously we have got, let's say fx equals to something, right? Fx equals to something, then you use f dash of x, okay? And then that will be equal to something. If you have y equals to something, and then you would use dy over dx equals to that something. Now, if you don't even have fx or y, if you just have, let's say, derive x squared or d over dx of x squared plus 1, for example, right? Then the notation is you just write d over dx equals to, because there's no y and there's no fx. So just say, right, d over dx, so that just means the derivative of the x function that we all know that is that function there is equals to whatever. So that's 2x in this case. Okay, so there are 3 scenarios. And again, number 1, if you see fx, you use f dash x. Number 2, if you see y, you use dy over dx. And if you see nothing, then you use d over dx. Now, you can actually interchange between these. For example, right? Say that one there for question A here. You see how they ask you to find dy over dx? So technically, you if they ask you to find that, then right. I'll use a different one. Look, dy over dt. So what does dy over dt mean? So dy is differentiate y. Differentiate y, and over dt means with respect to. So this is important. This with respect to is very important. With respect. Right, with respect to the variable t. Okay, that means that the t is the main variable. Okay, why is that important? So for example, I'll use question B as an example here. Y equals to t squared. Then dy over dt. So you differentiate y with respect to t. That would be just 2t, because it's like the same rule where you bring the power down and then you subtract the power by 1. Right? So you're not working with x, you're working with y and t. Make sense?
So then what's dt like?
With respect to t. Okay. So
it's not a fraction.
It's not a fraction, no. It's a notation. Now pay attention. This next one is very important. You will see this later, but I'll tell you guys now since I think you guys are ready for this. So what does it mean by with respect to? With respect to. Right? What does that mean by that phrase? It means the variable that you are deriving with respect to is the variable that is the main variable. Every other letters is a constant. What does that mean? So let's just say y is equals to ax squared plus bx plus c. This is a simple quadratic expression, right? Have a look. Ax squared plus bx plus c. If you were to do dy over dx, the standard one, what do you think the answer is? Remember, so this is with respect to x means x is your main variable, which means the answer will be?
Like 2ax.
Yes, 2ax
B.
plus b, right?
Yeah.
Yeah? But if you were to change that into dy over dA, what do you think the answer would be? Differentiate y with respect to a. What do you think the answer will be? Remember, if with respect to a, everything else, every other variable is just considered a number, considered a constant. What do you think the answer will be? It's a bit tricky.
2a.
Is just a.
You forgot the a in red one.
The red one? No.
Isn't it 2ax?
No, because remember, if you write it this way, right? over dA, right? That means y equals to x squared times a. Remember, x squared is now just a number.
But what about in dy over dx, isn't it 2ax?
The sorry. You mean the last one? Yes, it should be 2ax. My bad. You mean that one, right?
Yeah.
Yeah.
So
Then that's 2ax, correct.
dy over dA, like how does that work?
So how does that work? Means how does that work? Is so first you have to change the equation. Imagine it looks like this, right? Plus bx plus c, like that. The main variable now is a.
So then you're just focusing on what is like occurring to a.
Yeah, what's the power of a? Everything else is a constant, which means that's a constant, it's gone. That's a constant, it's gone.
Yeah.
And this is just a number, right? So that would be, so remember when you have like 3x, it just becomes, oh, hang on. Yeah, 3x becomes 3, right? Yeah? So now x squared times a, yeah, that should become x squared, my bad. That should become x squared. So it would be the x squared is like the coefficient of a.
Okay.
Does that make sense? Because x is now considered a constant, like a number.
Okay.
Does it make sense?
Yeah.
So that's what it means by with respect to.
So instead of it being like 2ax, it's whatever like
The coefficient of a
power
is.
of a.
Yes, the power of a. Yes, correct. That times down. Okay, and then you drop the power of a. Does it make sense, Sarah?
If a is the constant, then like why are bx and c also the constant?
Oh, you mean like for this version, right? Or like the one below? The one below. If you're saying differentiate with respect to a, then a is a variable, everything else is a constant. Right? So x is a constant, b is a constant, c is also a constant. It's similar to this one here. If x is a variable, then you got variable x, everything else, a, b, c, all constant. Yeah? So, okay, this is a bit of an advanced concept. So you won't see this until a little bit later when you see a complex unfamiliar question.
So for 6a, like in the worksheet, is that just -1 then?
Yeah, -1, yes. Yeah, because that's just with respect to x. So most of the time, you will find that the main variable will be x or t, most of the time. Okay? The remaining of the time, you see like a weird symbol is when you have a complex familiar or complex unfamiliar questions. Most of complex unfamiliar questions in these chapters, they will give you like v and h or h and a or something like that.
So for the ones that are like dy on like over dx, it's just whatever the derivative is, just like.
Yeah. So it's just x is the main variable. You derive it as usual.
Okay.
Yeah. Just pay attention to when you have like dy over d something strange. For example, see this one there. This one dz over dx. So you differentiate z as the main as like the y value with respect to the variable is x.
So it's just the same as before.
Same as before.
Z.
Yeah. We just got yeah. Okay, and
so
this
if
one.
we had it like, you know when you did your example with a, if that was like b, then it would just be.
Yeah. What do you think? What do you think if it's b? What if it's?
It would be like just x, right?
Yes, correct. Yeah, dy over db would mean just x, yeah, because x is a constant of the variable b now, because we are doing with respect to b, and all the other ones are constant. So ax squared is constant, c is a constant, they're all gone, and then bx becomes just x. Okay, so again, this is a bit of an advanced concept, so I'll just mention that now. Most likely you'll forget that in the next few weeks, but when I mention that again later, it will jog your memory on this. So yeah, just so that's it. If once I've explained example 9 and 10, you can do like almost the remaining of the question. So just start on question 5 and keep going.
For 6d, would you like expand the bracket first?
Yes, correct.
So
Oh wait, 6d?
Yeah.
Not for 6d because it's a constant number times into the brackets. So you can ignore that. You derive
So
everything in the brackets. You only expand it if the factor is like 6e, for example.
Okay.
Yeah, 6e is like x plus 1 is a factor, so you have to expand it because the factor is not a constant. It just has x in it. Same with 6f. Right? And 6g is an interesting one. See if you can do that.
And same for f as well, or would that just be 2 times 3x squared minus 4?
Same for f as well. You normally would expand it because the factor has x in it.
Okay,
It's
but
2x.
If it's just like 2, then I just ignore it.
Then you ignore it, yeah. You just times it in. Make sure you times it in, yeah? So just ignore it when you're doing derivative, but it should be there in the answer. Does it make sense?
Yeah, so do I do like 2x times 3x squared minus?
Yeah.
Yeah.
Wait, let me quickly check your 6D. Which one was it? This one, right? So 3x squared minus 3r. So the 1/3 is still there. It's 1/3 times this whole thing in the brackets. So you're ignoring it, but you can't leave it out. Does it make sense?
Okay.
Yeah. So 1/3 times into the brackets. Yeah. Because that's a constant number. So most of the time you can just leave it out like that. It's just factorize out. But if it's if you can times it in and it simplifies the number, then you times it in, simplify the
And I
number.
just divide them by 3.
Yeah. In which case you should do it for that one, and then it will become more simple.
So then, would I just do the derivative of this, or would I have to?
You have to times it in
first?
because that factor is 2x, right? So that has x in it. So you have to times multiply that one in. Later on, you will learn a rule where you don't need to do that, but for now, just expand the brackets. You learn some more rules in chapter 18 later next week. Okay, I'll just do some representative questions only. I won't do all of them. Any questions, Sarah?
For g, I would like cancel out the x first, right?
Correct.
And then, okay. But if I did that, wouldn't it just be 0 then?
No, it wouldn't be.
Because if I cancelled it out, and then it's like 10x3 and 3x2, then at the bottom...
3 over 2x2. Because you're dividing by 2x squared. Unless you're only dividing by x squared, but not the 2 at the bottom. Depends on how you want to do it.
But if I do 2x squared, then do I divide 3x4 by 2x squared? Because then it's like...
Yeah.
Then it's not a nice number.
Not nice, but you know, that's okay. When you work it out, it will become nice. Okay, so I'll show you 2 versions of question G. So for question 6, I'll do a few examples from D onwards. D, E, F, and G.
What question are we doing now?
Just keep going. You should be able to, yeah, just after 6, just 7, 8, 9, 10. Did you get 7G, 6G, right?
Yeah.
Okay, then just keep going, yeah. Any questions, Sarah? Yeah, which one? Oh, yeah, okay. So this is minus 1 times x. So the coefficient is minus 1. Right? Which means if it's a linear, so this is a linear equation, right? Because the power of x is 1, right? Which is essentially, when you derive it, it's just a constant, the coefficient of x, which is dy over x, which is just be negative 1. Yeah, make sense?
How do you like write down?
So if you want, you can write the next line, which is like this, right? Minus 1 times x. So then dy over dx equals minus 1, that's it. That's all you need to write. Right,
For 7b,
yeah,
once I like expand the first one and then I multiply it by t plus 1,
7.
7b.
Oh, yeah. Mm-hmm.
Is it 43 or 42?
So hang on. So when you expand this one, right?
Yeah, I expanded that one's all expanded, and then I just forgot to put that down there as well.
Oh yeah, you have to times this whole thing with t plus 1. So you have to do that whole, times it by that.
Yeah, so once
yeah.
I expand it, I have to times it by t plus 1.
Yeah, but in the brackets. Yeah, without a bracket, that'll be wrong.
Okay.
Yeah.
Okay.
Mm-hmm. That'll be like 6 terms in total.
So then it's 42 times t.
It's 40 cubed, yeah.
Yeah, okay.
Yeah, okay. Just keep multiplying them in. It's just a really long question, that's all. Okay. So yeah. So when you have a y equals to a constant term, the derivative of any constant term is just 0. So that one is not 0, so y equals 10. Now dy over dx will be 0 because there's no x in there. Right? So when you derive a number, a constant number, it's just 0.
Can I add these together or not?
Hmm?
Can I add 43 plus 42 or not?
No, not these two, but you would add these two together.
Oh, okay. Sorry.
Yeah. So make sure you do one with the same power only. Charlie, have you seen this notation? Let me see. How are you writing that? Y equals to... Oh, they're tiny, right? X equals to 2, y equals to... Yeah, okay. Now, there is a way to write the y value when x equals to... Sarah, have a look. So for question 10, when you're trying to... So question 10, right? You're finding the y coordinate and the gradient of the tangent line, right? The gradient of the tangent line is... okay, I'll show you guys my preferred writing for this one. So the first one, actually, I would cast this, and I mentioned to you guys earlier where you can change from y to fx. This is one of those ones where you can do that. So let fx equals to x squared minus 2x plus 1. Okay, that one line changes everything because then the notation is a lot easier. You can just go f of 2, that's a y coordinate, right? And then you can calculate f dash x, which is whatever that is, and then you calculate f dash of 2, and that would be the gradient. Okay, so the trick is to convert the y equals to into the fx, but you need to call that fx. You can't just use fx straight away. You have to go let fx equals to this. So that's the new procedure for you guys to do for question 10.
Okay.
Okay, so do that. That's mathematically correct. And another shorter way to write it is you go let fx equals y. Okay, because in these equations you have the y already, so you don't want to repeat the equation. You can just go let fx equals y. So that's a slightly shorter way of casting the y into fx. And then after that is continue as usual. Any question there, Sarah?
Why did you like have two?
This one?
Is it because x equals 2?
Yes, x equals 2, yes. Yeah, so you sub the x equals 2 into the fx equation. Let's see. So yeah, okay. And then you need to find two things, right? So one is the y coordinate, and you're gonna find the gradient of the tangent, which means you derive it and then you sub the x value into the derivative as well. Yeah. So yes, y coordinate is 1, and then the gradient on the right hand side there. So that's still question 8. So you have to derive it, find f dash of x, and then you substitute into that to find the gradient. Right? So they ask you for two things, the y coordinate and the gradient of tangent line. Okay, so just to let you guys know, in the exam, normally you need to make a final conclusion. Yeah, so y coordinate is something, and then gradient is something. It's safest to make that to write the final conclusion rather than just leaving it as like the values, like what f or whatever. Yeah, so make the final conclusion. Ideally, that's what you should do in the exam. But yeah, just for the sake of practicing, sometimes I will just be a bit more lenient. Are you on F?
Yeah.
Okay. Okay. So note that this one. Okay, so yeah, so note this one. So you expanded it, right? Which is correct, but the expansion is for fx. So notation wise, this should be fx equals 2, right? Because it's still the original function. You haven't derived it.
Yeah.
So after the expansion, so fx equals 2. You see that one there? It's still fx.
Yeah.
And once I have expanded that, then I write f dash x equals to the derivative. So this is not the derivative. That's why notation wise that's wrong. So just make sure your notation is correct. Okay, finish whatever question you guys are on, and that's it for today. That's the end of chapter 18C.